So here we are in section 4.4, indefinite integrals and the net change theorem. So I mentioned a while ago that we would be talking about indefinite integrals, so those are going to come back. So we've talked about the antiderivative, and that is the integral of f of x dx as one example, and that is some antiderivative f of x, and then here it is, plus c, and with the reminder that f prime of x is the little f of x. Okay? So our antiderivative here is this big f of x. This is what's called the indefinite integral, and it makes sense because the idea here is we don't have limits of integration. We are just finding that general antiderivative, and of course adding c to the end since it is a constant and could have been there before a derivative was taken. So a couple notes on the indefinite integral. We have the first note, and this antiderivative is a function, and as we've already said, the derivative is this little f of x. Okay. And when you put those limits of integration, we've already talked about that this value is a number. And when you do the limits of integration, you have various interpretations, meaning it's a number that can represent things, and we've talked about how in the beginning this would be the limit of sums of the rectangles, that if you added up an infinite number of rectangles underneath a curve, you would get that same number, which then leads into the idea of area. And there are actual more values. We did talk a little bit as well about like total distance in one of the earlier sections. So the connection here, of course, as we talked about in the last section, just as a reminder, is that this is taking that antiderivative and evaluating from a to b. So we've seen that stuff already in previous sections. So it's just a reminder. And now what you're going to see here is basically almost the same exact thing that you saw on page, from section 3.9 when we did antiderivatives. So the only difference between what we did in 3.9 and what we're doing here is that now we're more formal. We're using the integration sign, we're using that differential of the dx. In this case, all of these are, they're all functions of x here. But now they're just like what the rules are. So if you want, you could go back to section 3.9, see what we wrote there, see how many of these you can fill out. But the idea is, I'm just going to use the same rules here. This is the idea that we can separate integrals that are multiple terms into pieces and take the antiderivative of each piece. We can integrate each piece separately. You probably remember the second one here is to take the antiderivative of x to the n. We're going to add 1 to the exponent, and we are going to divide by that thing. Okay, we're going to add c to the end of these. This is true as long as n is not -1. I won't spend too much time on that idea, but basically the antiderivative of 1 over x, which is the same as x to the -1, has a very special antiderivative, which is not talked about in the 5a course. So you won't see that until you get into 5b. But if you want a hint, it is the natural log. So just wait. All right, antiderivative of sines, we want to think about what do we take the derivative of, in order to get sine, and that's going to be a negative cosine plus c. So again, you're welcome to think about what these are, put some answers, and then come back and take a look at what I'm doing. So here, cosecant squared is going to be cotangent plus c. And then we also want to think about the fact that this is going to need to be negative in order to get, because the derivative of cotangent is negative cosecant squared, so negative is a positive. These are all things you should know off the top of your head. You should not have to look in your notes for the derivatives of sine, cosine, tangent, cotangent, being able to go back and forth on those trig functions and their derivatives is really important. Up at the top here, this is a constant, any real number. And so just like so many other things we can pull that out. And don't forget to add C. Here we have just K. And K is another example of just having a constant. It's just a different constant because I already used C above. And the idea there is the antiderivative of K, the constant, is going to be Kx plus C, meaning that, because you take the derivative of something times x and it's just that something, whatever that number is. Basically the idea that right there you have k times x to the 0, and then adding 1 to that is going to give you an x to the 1, or x. All right, antiderivative of cosine, we've already talked about this. This is going to be sine x plus c. And then these should look familiar as well. This is going to be a secant x plus c. And then here we're going to have a negative cosecant x plus c. So again, those idea behind the negatives are that if you're taking the derivative of what I have on the right side of these, you should be able to get what we have on the inside. And the derivative of cosecant is cosecant cotangent, but it's a negative. And so in order to get the positive inside the integral sign, I need to have a negative on my cosecant on the right hand side, so that if the derivative was taken, I get what I started with. So remember that there's that relationship between the two, differentiation and integration. So those are all of our rules, and just in that more formal way using the integral sign. Okay, so now we're going to do some examples of integration here, and it's the definite integral, so it's really the same as the idea of antiderivatives, but in that more formal way. So notice how I use my notation here. I'm not going to say things are equal unless they are. So I'm going to rewrite this, and this is really important. At this point, we do not have any fun, funky, tricks up our sleeve in terms of taking integrals. And so because of that, we just have to stick to rewriting and using the integration rules that we have on the last page. We don't have anything too exciting. So I have 4x to the 5th, and then plus x squared, x to the 5th, and then that's going to be dx, and that's going to give us 4x to the negative 5 plus x to the negative 3. So I'm just rewriting this so that I can get to the point where I have something that looks like those integral rules. Because now I have two pieces that each are x to the n. And the 4, okay, I can do different things with that depending. I will not expect this every time, but if I were to say use the integral rules, your next step would be then to separate them. So you're showing that you understand that this is a right that you have using the properties that we have. And then now let me come down here. Now I can take the antiderivative of x to the 5th. So I'm going to add 1, and then I'm going to divide by that thing. And so I'm going to divide by a negative 4, which is a negative multiplying by a negative 1/4. And close that up. Then I'm going to add what I get here. So I'm going to add 1 to my exponent, so negative 2, I'm going to divide by that thing, so I get a negative 1/2, and then I'm not going to forget, I should have a plus c at this point, because I've now taken my antiderivative on both of those pieces, and my antiderivative always needs to have that constant that could have been there, because this is a function. I can do a little bit of simplification here. It looks like I'm going to have negative x to the negative 4th, minus 1/2 x to the negative 2 plus c. And it's up to you. If you really want to write this as a negative 1 over x to the 4th and a 1 over 2x squared, that's fine. These things are equivalent, so either one is okay. Just make sure you don't do some weird combining, or you got to be careful. It's got to be right. So that would be our final answer right there. For the second example, notice that you have sine theta, you've got cosine theta squared. These are not things that you guys know yet, just in terms of, what do I mean by that? Like you don't have an antiderivative of cosine squared theta. Like that's just not something that you know the antiderivative of. And you can't, you know, we do not have at this point some sort of like product rule or quotient rule for antiderivatives. So you can't just take the antiderivative of like the numerator and try to take the antiderivative of the denominator and just, okay, that's just not an option you have. All you have are the rules from the last page. So what I would do in this problem, and this is a very smart trick for anything with trig functions, is you're going to have sine theta over cosine theta. This would be an option, times 1 over cosine theta. So I'm going to separate them. Notice I have a d theta because that's telling me that I'm taking the integration with respect to theta. And do this. And so this rewriting is, my thought is just like, is this going to give me something that I'm familiar with? And so we can see that a sine theta over cosine theta would be a tan theta. And a 1 over cosine theta is a secant theta. And now, hopefully what you see is, oh hey, tan theta, secant theta is the same as secant theta, tan theta. That's multiplication, so it can be done either way. And I know that the antiderivative of that is my secant theta. So now I'm ready to do secant theta, and then of course my plus c to show that I've taken the antiderivative. And then I'm done.